Yes, students, next topic is crystal field splitting in tetragonal and square planar complexes. The splitting of d orbitals in tetragonal and square planar complexes that can be explained by the splitting of d orbitals in octahedral complexes. Means we can explain splitting in square planar and tetragonal with the help of octahedral complexes. As in octahedral complexes, firstly 5 degenerate orbitals of free metal ion, then all the ligands, 6 ligands are approaching to the central metal ion at equal distance, and due to different shapes of the d orbital, there is splitting of d orbitals into two sets, that is one is Eg set and second is T2g set. T2g at lower energy and Eg set at higher energy. Then in this we consider that we take two trans ligands. For example, this is the octahedral complex. In this two trans ligands, as example, we take along the z axis. If we take two trans ligands along the z axis, we withdraw two ligands along the z axis, means then distance between the metal and ligand along the z axis increases, whereas metal ligand distance along the x and y axis, this is the y axis, this is the x axis. So in this metal ligand distance along the z axis increases, whereas along the x axis and y axis metal ligand distance decreases, and this is the tetragonal structure. Two trans ligands are at large distance, and finally we completely remove two trans ligands along the z axis, and this will be square planar complex in which two trans ligands are completely removed. Then we will discuss how crystal field splitting in tetragonal complexes. As two trans ligands along the z axis are withdrawn, or we can say the metal ligand distance along the z axis increases. Then along the z axis orbitals, for example dz square orbital, then the repulsion between ligand and the metal dz square orbital having electron, that decreases because metal ligand distance decreases. As the repulsion between the ligands and the dz square having electron decreases, then energy also decreases. So, and as we know that along the x and y axis the ligands come closer to the metal ion and distance decreases. Then due to the close distance between the metal and ligand, there will be more repulsion between the ligands and metal dx square minus y square, that is along the axis, and therefore their energy increases because there is more repulsion as compared to dz square. So Eg orbital, Eg set in octahedral complex that contains dz square and dx square minus y square. So dz square orbital having lower energy and dx square minus y square orbital is having higher energy. Then in T2g set also three orbitals dxy, yz and dzx. So along the z axis the repulsion will be less because metal ligand distance along the z axis is greater, so repulsion will be less. So dyz and dzx orbital will be having lower energy, and along the dxy plane, that is having higher energy. So there will be splitting, and this is the splitting, dyz and dzx having lower energy and dxy having high energy, and Eg set dz square having lower energy and dx square minus y square having high energy. So this is the tetragonal splitting. So this is the tetragonal splitting. Next, as we withdraw ligands completely along the z axis, then there will be square planar complex. Then along the z axis there will be less repulsion, and energy of dz square also again decreases, and it decreases even than the dxy, and dx square minus y square, as they come more closer to the central metal ion, so there will be more repulsion and their energy increases. So dx square minus y square energy further increases, and dz square energy decreases such that it even decreases below the dxy. Similarly, below to dyz and dzx energy further decreases, whereas dxy energy increases even greater than the dz square. So this is the crystal field splitting in square planar complex, and there is distance between the dx square minus y square and dxy, that is delta sp, that is the square planar splitting. So this is the square planar and tetragonal splitting. Further, as we withdraw two transligands along the z axis, we can also, this is called elongation. If we withdraw two transligands along the z axis, that is called elongation. If we withdraw ligands along the x and y axis, if we withdraw ligands along the x and y axis, then this is called flattening. Then the order will be reversed and there will be crystal field splitting. So in tetragonally distorted and square planar complexes, so one will be elongation, other will be flattening. Next is crystal field theory and magnetic properties of the complexes. As we know that there are two magnetic, according to magnetic properties, there are two types of substances. One are diamagnetic and there are paramagnetic substances. Diamagnetic, in which there are paired electrons, and paramagnetic means there are more number of unpaired electrons. So this can be explained on basis of crystal field theory. If delta O is greater than P, means crystal field splitting is greater than pairing energy, then the electrons will prefer to pair up and there will be low spin complexes, and this will be only in case of strong field complexes. And if delta O is less than pairing energy, then there will be more number of unpaired and that will be high spin complexes. So there are two types of complexes, strong field complexes and weak field. Strong field will form low spin and that will be diamagnetic, whereas weak field complexes more number of unpaired and are high spin complexes and that will be paramagnetic. In this we take example, for example cobalt ammonia complex and cobalt F6 negative. In both, cobalt is having +3 oxidation state in both complexes. Cobalt +3, cobalt is having atomic number 27, 3d7, 4s2 and cobalt +3 oxidation state. So electrons will be removed from 4s and 3d and there will be configuration 3d6 in case of cobalt 3 positive. So both are having cobalt +3 and d6 configuration. So in this, ammonia is a strong field ligand as compared to fluorine, so fluoride ion. So it will form low spin complexes, whereas fluoride complex that will form high spin complex. So in this there will be no pairing of electrons. So firstly electrons filled into T2G, 3 electrons below, then 2 electron goes into EG set and 6th electron automatically paired. So this will be having unpaired electrons, so this will be paramagnetic. Whereas in case of cobalt ammonia 6 positive, that is having 3d6, so d6 6 electrons that get paired into T2G, so that is having T2G6 configuration, all are paired, so that's why it is diamagnetic. So these are the diamagnetic and paramagnetic substances. So that depends upon the delta O and P, that is the strong field complexes and weak field complexes. Thank you students.